Hi, in this video I want to go back to looking at a problem in Broverman's book. We're going to look at a modified version of exercise 7.1.3. The directions of the problem in the book say this: use a spreadsheet to repeat example 7.2 where we find the Macaulay duration of a bond for different parameter values that you see here. R is the periodic coupon rate, N is the number of coupon payments, and J is the periodic coupon yield per coupon period. And then we're going to consider in a spreadsheet holding two of the three parameters R, A, and J fixed and identifying the behavior of the Macaulay duration as a function of the other parameter. Okay, so we'll consider what happens when R and N are fixed and let J change. We'll consider what happens when R and J are fixed and let N change, and we'll consider what happens when N and J are fixed and let R change. I'm modifying this problem a bit. I'm adding some extra directions. I also want to use Mathematica to identify the behavior of this thing as a function of the other parameter while holding the other two fixed with graphs, actually. And we're going to see with the graphs that sometimes the behavior is what you might say unexpected. The Macaulay duration is it's a pretty confusing thing to understand in its full generality, even in the situation where we have a bond that's going to be redeemed at par. It doesn't say this bond is redeemed at par, but that's going to be the assumption that we're making since it's not stated otherwise. We're going to see some pretty subtle things, and I want to give some financial interpretations to those things, pretty unexpected things, and I think that's going to be a cool thing that you're going to see in this video. So what are the goals for the video? First of all, review the formula for duration, and I'm going to show you that you can also simplify it for the situation for coupon bonds that are redeemed at par. Secondly, we want to show how to solve the problem as stated in the spreadsheet. So that second part is where we're actually solving exercise 7.1.3. with this spreadsheet that you see. And third, show graphs in Mathematica to understand the behavior of duration. Before I get into the details, let me also say that duration is again sort of a measure of average length of a bond with respect to when payments are made and what the present values are of the different payments, what their relative sizes are, and what the yield rate is, all affect things. And intuitively, if you look on like Investopedia, they talk about this in terms of duration risk. When the duration of the bond is greater, a greater number of years, your risk, both positively and negatively, to changes in interest rates is greater. If interest rates go up, that's going to mean the price of your bond is going to go down, and it's going to go down faster if the duration is higher. And that, if you want to sell the bond, is a bad thing, right? If you want to sell it, you got to sell at the current market price. If the interest rates are going up, your bond price is going down, you're not going to be able to sell it for very high. And again, the bigger the duration, the greater that price is affected by changes in interest rates or yield rates. On the flip side, though, if the interest rates go down, then the bond price goes up, and if you want to sell it, that's good for you. Okay, so that's an important thing to realize as well. Note in this situation that the formula for the duration can be written in terms of present values of annuities. We have your A and J, your present value of your standard annuity with payments of 1. We have the I, A, and J that you see here, present value of a standard increasing annuity. The formula can be written this way. Let me show you that first, that derivation here that I've got here in this Mathematica notebook that I'm looking at now. For bonds with coupons FR, so F is the face or par value, R is the periodic coupon rate, F times R, of course, is the coupon amount. Redemption value, F, is the same as the face value. That's the assumption here to make things simple. Yield rate is J, could be called I, many people call it I. Here is the definition of the Macaulay duration over here as this ratio of these two summations. If you think about this with timelines, as I've done actually in recent videos, you can rewrite this ratio in this way. We've got the bottom really being the price of the bond. This is the standard basic formula for the price of a bond. And the top, the numerator, because of this extra factor of t, that's why you get the extra I, A, and J in there instead of just a plain A and J, and why you get the extra factor of N right there. There's an F in every term, however, so the F's all cancel. And you can simplify the formula to this, which is exactly what you see in this spreadsheet right here. Take a look at this. Maybe pause the video, write that down. Now let's go back to that Mathematica again, and I'll show you it really is the exact same formula. And then just to realize you actually can simplify this so that it's just in terms of R, j and n and no a's or iA's at all. Though it is a bit tricky, you can use the formula for a and j right here. To do that substitution, you can use the formula for ia and j and do this substitution. This thing right here is really a double dot. Notice it's the same as a and j times 1 plus j. We've got the minus n times v to the n that's in the formula for ia and j, all divided by j here. And then, this compound fraction can be simplified. You could, because you've got a j here and a j right there and right there, it's best to multiply the top and the bottom by this big fraction by j squared, so that both j's here and here cancel up on the top. You got to do it to the bottom too, and if you simplify that, you get this. And then you could leave it like that, but you could also get rid of those negative powers of 1 plus j. You can essentially convert the 1 plus j's to negative n's to 1 plus j's to positive n's if you want. So what I did next is I multiplied the top and the bottom of this fraction by 1 plus j to the positive n and canceled all these 1 plus j's to the negative n's that you see here, and wrote the formula this way. So you could pause the video, write that down. That's a pretty complicated function of r, n, and j. It can be entered into Mathematica, and we're going to make graphs later. For the moment, no. Let's go back to the spreadsheet and do part 2. So I've essentially done part 1 now. Reviewed the formula for duration and simplify it for coupon bonds redeemed at par. Let's look at part 2 now, which again is the main thing you're supposed to do in exercise 7.1.3. So I was trying to think about how best to do this, and it's kind of complicated. So what I'm about to do is I'm about to use these formulas that you see here on both these lines and these spreadsheet cells that you see here. I'm going to use formulas in spreadsheets. I'm going to use equal signs to do math. I'm going to use cell references to take numbers like, for example, j. I'm going to initially put 0.03 right there for j because that's the first value j that we're given here. And I'm going to compute these different things. I'm going to compute a and j and ia and j. And then use the different coupon rates and different coupons till maturity that we are given up in this description up here to fill in durations that go in right here. The Macaulay durations are going to go in these spots right here. And we'll see that for fixed j, what happens as r increases by going down the table for these different n's, and what happens as n increases by going across the table for these different r's. Like that. That'll help us identify what happens as j and one of the others is fixed and then one of the others is increasing. And then I'll be able to see what happens when j increases by keeping r and n fixed, seeing the numbers in the table and changing this number right here. And if I've done everything right with my spreadsheet formulas, we should see things get the correct numbers, and we should see things get updated, for example, as I change j. But this is pretty tricky. So you're going to want to pay good attention. I'm really going to assume you've used spreadsheets to a certain degree here, because I'm going to go kind of fast. If you've never used a spreadsheet before, it's probably going to be too fast for you to follow. But I'll do my best here to explain it as I go. So first I want to use the formula for a and j right here, 1 minus v to the n over j, and use spreadsheet cell references. For example, j is in cell F13, column F, row 13 here. And I'm going to use dollar signs going in front of the letter to keep the column fixed when I want to keep it fixed, and in front of the number, like the 13 or 14, the rows, to keep that row fixed. And there might be some situations where I don't really need dollar signs where I put them, but to keep it clear in my mind and hopefully avoid mistakes, I'm going to maybe overuse dollar signs to a degree. Sometimes I might use dollar signs in front of both the letter and the number, even when I may not need to, okay? Just to help me avoid mistakes, because it's easy to make a mistake with this. Okay, so let's use this formula, 1 minus v to the n over j. So I have parentheses, because I'm going to divide all this thing by j. 1 minus, what's v? V is really 1 plus j to the negative 1 power. 1 plus j. J is in cell F13. Now I'm going to want to copy and paste this to the right. I'm going to want j to always come from cell F13. I'm going to play it safe and use dollar signs in front of both the F and the 13. Copying and pasting to the right technically would keep the 13 fixed because I'm staying in the same row, but could change the F to a G to an H to an I. So really I only need the dollar sign in front of the F. But to play it safe here, I'm going to use it in both spots. But there will be some spots where I only use it in one spot, as you'll see here. So it gets a bit confusing here. I need a negative power because, again, v is 1 plus j to the negative 1. I want to raise v to the n, which is down in cell F18 down here, but I need that negative sign because, again, v is 1 plus j to the negative 1 power. Okay, this is in cell F18 down here. What will happen if I put just an F18 without dollar signs and I copy and paste it to the right? That will be okay because the 18 will stay as it is because I'm copying and pasting to the right. I'm not pasting downward, so it would not become a 19 and a 20. And the F, I do want to get updated actually for this one to being a G18, then an H18, then an I18 as I copy and paste this formula to the right. So I do not want a dollar sign in front of the F there. All divided by J, which is in cell F13, and I want that to stay the same, so I'm going to play it safe and use $2 signs. Okay, this should make some sense, and you could check it with your calculator. Or maybe I'll even check it over here by actually typing numbers here. 1 minus 1.03 to the negative 2 divided by 0.03. Yes, that is a little less than 2. That is the present value of a basic annuity immediate with payments of 1 at times 1 and 2 with this particular yield right here. Okay, as I copy and paste this to the right, it should be all correct. I have no proof that these numbers are right unless I just double check them. Like maybe let's check this last one when n is 40. Replace this negative 2 with a negative 40. And yeah, that is correct. It looks all good here. Okay. And these numbers are all less than the corresponding value of n, which should make sense. It is interesting, and maybe you already knew this, that the ratio of this a and j divided by n gets smaller as n increases. That's something you should probably know from the past. Okay. All right, now what about IA and j? I'm going to use this formula that you see here. Notice that this formula involves a and j, so I can use these numbers to help me calculate these numbers. But again, we got to be careful. Okay, I'm looking at this formula. I want to use parentheses and be careful. I have a 1 plus j. J is in cell F13. I want that to stay the same. Times a and j. I can just click on that. That's F14. If I copy and paste this to the right, I want that to get updated to G14 and H14 and I14. I definitely don't want a dollar sign in front of the F. I could put a dollar sign in front of the 14, but I don't need to because I'm just copying and pasting to the right, so the 14 would stay as a 14. I'm not copying and pasting downward. Minus n, which is in cell, again, F18, and again, I don't want dollar signs there. I want that to get updated to G18, then H18, then I18, times v to the n, 1 plus j to the negative n, and I want that to get updated. Hopefully I've got the right number of parentheses here. That's another issue. I think this looks good. All divided, again, looking at this formula here, divided by j from F13. Okay, so these are going to be present values of increasing annuities with first annuity immediates with first payment of 1 at time 1, 2 at time 2, 3 at time 3. These numbers are in general going to be bigger than the numbers above them. Yep, that one's bigger. And yeah, that one's a lot bigger than that one. Okay, as n increases, the ratio of this thing to this thing keeps getting bigger. Okay, and that's something you probably should have known from the past as well. All right, you still with me? Take a deep breath. Let's go down to here. I hope you're getting a lot out of this video. I think there's a lot of good stuff in here. Now I want to use the formula for the Macaulay duration here that we see here for these special case of a bond, a coupon bond redeemed at par. So I want to use these numbers. And I got to be careful. And I need to use these numbers here and these numbers here. And I want to be careful that what I do is copy and pasteable in a nice way so I don't have to keep retyping things. I think thinking strategically here, I'm going to put the formula here in cell F19, and first I'm going to copy and paste downward. So I want the right things to go in these cells based on our changing. And then I'm going to take that entire column and copy and paste it to the right. And I want all the right numbers here, okay? So this is a little bit scary here that I'm going to make a mistake. Let's see, so we don't want to use parentheses here. All right, let's just take it carefully. I see an R times IA, NJ. As I copy and paste downward, I want the R to change, so I want the row to change, but not the column, though since I'm pasting downward, it would automatically not change. However, as I copy and paste to the right, I do not want the column to change because I still want to use those values of R. So I need the column to stay fixed. I need a $sign for sure in front of the E. Okay, so I have E19, that's the value of R that I want there. I'm looking again at this formula for D that in red up here. And I want a $sign in front of the E, but not the 19. I want the 19 to get updated to a 20, then a 21. But the E needs to stay the same as I copy and paste to the right. Okay, I think that's right. Now let's get the cell reference for I. That's in F15. There I need a $sign in front of the 15. Can you think about why? I want, as I copy and paste downward, that to stay in row 15. But I don't want a $sign in front of the F because as I go to column G, H, then I want the number to go from column G to H to I as well from this present value of an increasing annuity. Here I want those to change. Looking back at the formula in red up here, plus N, which is in cell F18. As I copy and paste downward, I want that to stay in row 18. So I need a $sign in front of the 18, but I want it to change as I go to the right, so not in front of the F. Times V to the N, I might as well use $2 signs as I did before, just to play it safe. J is always going to come from F13. To the negative N power, as I copy and paste downward, I want that to stay the same row, but not the same as I go to the right, so F$18 again. Check my number of parentheses here. I've got the the numerator here of this fraction. Looks good, I think. I want parentheses again. R $E19 again times ANJ. Not INJ, but ANJ. I want to take from F14 here, but I want to, let's see, again, keep the 14 correct, but not the constant, but not the F. So I want F$14 plus V to the N. We're almost done. 1 plus $F13 to the negative N power. Running out of room here for you to see this. And again, coming from F18. Nothing in front of the F, but a $, in front of the 18. I think this should do it. Oh boy. Some mistake. Maybe I forgot parentheses. That's probably the problem here. And actually it's suggesting to me the correction. I think I forgot my last parenthesis there. Yeah, it looks like it. But it's added one here, so I'm going to click yes to accept this correction. There we go. And now I look up here and I see it's got the 2 parentheses there at the end. Okay. Let's copy and paste this downward. And now copy and paste it to the right. And hopefully all these numbers should be correct. Let's see, maybe we should take the time to check one of them here. Actually, I could check it with Mathematica. I'm pretty sure my Mathematica is correct. Let's check this one with Mathematica. J is 0.03, R is 0.08, and N is 40. Should get 19.97. I plugged this function into Mathematica. What was R? I forgot R. 0.08, I think. N was 40, and J was 0.03. I think that's correct. Enter that into Mathematica. Oh, ignore that. Why did it do that? Oh, Dmac, that's why. 19.9706. Yes, this looks good. Okay, 19.9706. So now I've essentially shown how to solve the problem in a spreadsheet in the sense of programming the spreadsheet. However, if you were solving this problem for real, if you're using Broverman's book, 7th edition or some later edition, you should now also describe the behavior of the Macaulay duration when you keep two parameters fixed and change the other one. Here we're keeping j fixed initially. If we look down the columns, we would then be keeping n fixed, and we see that as we let r increase. So we see as the coupon rate increases, the duration goes down. As you look at these columns, the numbers decrease as r increases. Does that make financial sense? Well, higher coupon rates are going to give you larger coupon amounts, and that's going to sort of weight in the weighted average, giving the duration, the average payment, so to speak, as a present value compared to the present value of the entire payment stream toward earlier amounts. The coupons are higher compared to the redemption amount than they are when the coupon rate is lower. So that's why, financially speaking, why these durations will go down here as r increases. Higher coupon rates give shorter durations. Okay, you're getting more money up front, and then that is less affected by changes in interest rates when the coupon rate is higher. On the other hand, if you keep a fixed coupon rate and increase n, this should make good sense. The maturity certainly increases, or the duration increases as n increases. You got more payments. You should expect the average time of payment, again weighted by present values, to be higher. However, it is interesting. The durations are much closer to the number n when n is small than they are when n is large. Okay, that's something to keep in mind. And I guess intuitively what's going on there, when you've got a large value of n, a lot of coupons, and then a final payment, that redemption amount, is way in the future. And especially if j is large, if you think about it, the present value of that future payment is going to be really relatively small. As j gets larger, that present value of that future redemption amount is going to get small. We should expect this relationship to be even more extreme when j is larger. Okay, and I'll look at that here in a second. Okay, so hope that makes some sense too. If you want to write these numbers down, you can pause the video. I think it would be good maybe to copy and paste these numbers. I'm now going to change j and see what happens down here, but I think I should paste special so I see the values instead of, I don't want to paste the formulas. Paste the values so we can see these, and that's going to be, just help me keep track of what happens now when j was 0.03. Here was what we saw when j was 0.03. Let's now increase j as is asked for to 0.05. What should happen? I mentioned this in the last video. As the yield increases, you're used to yield increasing, the price decreases, but as the yield increases, the duration goes down as well. Those payments that are further in the future are more greatly affected because v to the n has a greater effect when j is larger, for large n's. So we should expect the duration to go down as j increases. Let's see if that happens. Here I'm going to increase it to 0.05 and everything should get updated correctly. Yep, and numbers went down. You compare these numbers to these. These are smaller, okay? And again, the effect is more pronounced when n is large. Okay, it's not very pronounced effect when n is small, like 2. But definitely when n is 40, you can definitely see the durations are a good chunk smaller. Let's go ahead and copy and paste these. Down here, paste special, values. These are the numbers when j was 0.05. Now when j is 0.07, the last one, we should see them go down again. Okay? And once again, it's more pronounced when n is large. Okay? So that's something to put in the back of your mind. So essentially now we've done part 2 of the video. Now let's go on to part 3. Show graphs in Mathematica and understand the behavior of the duration. Okay? So we're going to look at some graphs, and we're going to see some interesting things. And it's a lot to take in, okay? And really, if you're really interested in this, you're probably going to want to rewatch this part a number of times to really try to take it all in. So what I'm first going to do is I'm going to plot the duration as a function of j, keeping r and n fixed, and just seeing what happens. Though Mathematica allows me to change it to r and n. So what I've got here initially is r is 0.04 and n is 2. And it looks like, for all you can tell, the duration is constant. Is it really constant? Constant as a function of j? No. It's just going down ever so slightly, like we really saw in the spreadsheet there when we're looking at the n equals 2 columns. There's not much difference between these numbers, but there is an ever so slight difference. However, as n increases, as I move this slider to the right, we definitely get something you can see visually as a decreasing function of j. This is now graphed as a function of j. But these sliders in Mathematica can be changed, and I can see the effect of these things. We also see that as r increases, as this slider moves to the right, the graph goes down. As n increases, the graph goes, well, up when j is small, though down when j is large. Interesting. That is really, really interesting. That's something perhaps unexpected. Is that really happening? N is increasing. Initially, the graph goes up no matter what j is. But when n is large, the behavior is more subtle. And we even see the graph going down as n increases for large j. Does that make financial sense? If j is really large, I mean, you never really see in real life 50% yield rates. Okay, maybe that's why people don't really expect this kind of behavior. I'm letting j go out to 0.5 here. If n is really large, this can go down for large values of j. Why would that be? Well, I think intuitively, those kind of values of j that are so high, like 0.5, 50%, that's going to make the present value of the redemption amount tiny, really. It's going to weight those coupon amounts that are earlier much more heavily. So even though n is large and getting larger, the duration can still go down when j is really large. That's something subtle and unexpected. But again, as r increases, the graph goes down, though the effect is greater for small values of j. R increasing has a bigger effect on the duration as your coupon amounts get bigger for small yield rates than they do for large yield rates. Another interesting thing to see. And another interesting thing to see is that for small r and large n, this graph has an inflection point. It's concave down here and then concave up there. Okay, you can emphasize that by even graphing its derivative. This graphs its derivative in blue. So this red graph is the graph we were seeing already, and the blue graph is its derivative, and you can see that the derivative has a minimum for this particular situation when r is 0.0254 and n is 16.26. Actually, I should let n only be an integer here. N is large. This graph, the derivative, has a minimum, in this case, at about 0.1. So there's an inflection point in the graph of the duration graph, the red one at about 0.1. Okay, something unexpected. You can give all these things financial interpretations. I'm not going to read this, though I do notice a typo, sensitive. But you could pause the video and write this down if you like, and then think about it. It's a qualitative description of what we were seeing here. Okay? Let's go on to graphing the duration as a function of r now, keeping n and j fixed. So now this is a function of the coupon rate. And we can look at this graph for different n's and different j's. Again, the graph goes up as n increases. And this one, no matter what j is, it's always a concave up graph. It's always decreasing as r increases, which again should make sense. Large coupon payments relative to a future redemption amount mean you're weighting your payments toward lower values, so you get a smaller duration. But this graph is always concave up, so the duration goes down fast for small changes in r when r is small to begin with. But when r is already pretty large, when you got really large coupons, increasing them a little bit more doesn't change the duration very much. If you increase n to being pretty high, then the effect is even more pronounced. You see this going down very fast at first, though for lower j it doesn't go down quite as fast. Okay, so some other things, maybe not quite as unexpected. It looks like maybe we have a horizontal asymptote here. This function does have a limit as r goes to infinity. It's that expression, which could be plotted in here as a horizontal asymptote for this graph. Okay. I don't know that this formula is ever very useful because the coupon rates don't go to infinity, but just mathematically speaking, it's interesting to think about perhaps, or for relatively large coupon rates, you could think about it. And this got some financial interpretations as well that I thought of. By the way, these financial interpretations are not the end-all be-all of interpretations you could give to this. But again, you could pause the video and write this down and think about it based on the graphs that I showed you. And finally, we're to now thinking about this as a function of n, and n is a discrete variable, 2, 3, 4, 5, 6, etc. So I'm making a discrete plot here instead of a continuous plot. This is actually the most interesting. Definitely an increasing function of n. Here when j is 0.04 and r is 0.04. But watch what happens as these rates change. As r increases, the graph goes down. And it goes down especially fast for small increases when r is small to begin with. When r is really small, the graph's really high, and r increases, it makes the graph go down pretty rapidly there for large n. But watch what happens if r is large and j increases as well. Actually, no, the other way around. If j is real high, but then r goes down, watch what happens. Whoa, isn't that wild? This graph has some sort of maximum at some sort of intermediate value of n as well. When r is low, the coupon rate is real low, and j is large, the yield rate is real high. The Macaulay duration can be maximized at some moderate value of n, and then as n gets larger and larger, it approaches some sort of horizontal asymptote. Does that make financial sense? Boy, I'm not sure. I think that's probably the trickiest one to think about. Why would the duration get smaller as n gets larger? I think in thinking about this here initially myself, I think once again when n is really large in this situation, we're talking about this situation with bonds redeemable at par, coupon bonds that are redeemable at par. Once again, when n is really large, you've got that future redemption amount that's way in the future. And even though it's the largest amount, and even when the coupon rate is small, it's definitely the largest amount. Its present value is relatively small when j is really high. And so I guess that's what you might justify as saying why the duration goes down as n increases. You're making that final redemption value so far in the future that even though the coupons are small, the overall duration goes down. There is a horizontal asymptote. This has got a limit too, and it's actually a fairly simple limit. Ignore this conditional expression stuff. It's 1 plus 1 over j, as the limit of that as n goes to infinity. And I guess, you can imagine bonds that have a large number of coupons more easily than thinking about r or j being really big. So this is probably a more useful thing. The limiting value of this is 1 over 1 plus j, and you can graph that in here and see it when j is relatively large and r is relatively small. Okay? And this got some financial interpretations that I thought of as well that you can copy down and think about. Again, these interpretations are not the end-all be-all of what we're observing. You could probably make more observations and interpretations, but these are things that I thought of, and I think it's pretty interesting, pretty unexpected, and maybe something that could be useful for you in the future. I think especially this last one. Thanks for watching.